Hi, everybody. I guess we can get started. Just a few things. If you haven't scanned your exam and submitted it to the PDF, do that as quickly as you can practically. Just a couple of announcements. The 8 homework is posted. This is the final homework that you'll have to do for the class. It's 5 problems on rotation, so things we've basically been doing this week. And it's due Monday, and then there won't be another homework next week. There'll be a number of practice problems, but every problem I will post next week will include solutions with it. So you can work them for practice, but you can also see the solutions. I'll have practice exam. I'll have a practice problems on the topics that we've covered, that we'll cover on Monday, and so forth and so on. The final exam is on Thursday, next week. It will run from 9:30 to 12:30. The format will be quite similar to what we're doing here, which is to say we'll start at 9:30. We'll all meet before 9:30. Make sure that you get the exam. The exam will be broken into 3 one-hour segments, well, roughly 50-minute segments, with a 10-minute break between each one to submit and then get the next exam. So it won't be all 3 at once. It will be an hour and then back, an hour and then back, and an hour and then back. That will be the plan. So it'll be like taking 3 little exams, one after another with a little break between them. The topics will be comprehensive, which is to say that the final exam would be just as likely to have a problem on rotations as it would be to have a problem on one-dimensional kinematics, the whole semester of material. Just so you know the plan for next week, Monday we're going to mop up a few things. We're going to take a quick look at gyroscopes. Not too much detail, but we've pretty much got the tools we need to take care of them. There's going to be one little thing with friction, and that is I'm going to let you see what limited things you can do with the coefficient of static friction. And then non-inertial reference frames, we'll touch on those. I have a couple of video clips that will go out over the weekend, so you can get a head start on that. Tuesday, we jump from the classical era to the modern era, which is to say from the 16th century to the 19th century. We're going to compare what we know about universal gravity to Einstein's gravity. A little bit of kind of a chance to look at about how they are similar and how they're different. What the relevance of it is for the evolution of the universe, ideas in cosmology and astrophysics. Wednesday is just review. I've got some interactive problems. I've got what are you call clicker problems. I've got a range of different things to sort of test primarily your conceptual, but also your tactical and technical ability to be ready, prepared for the exam. And then Thursday's the exam. Does anybody have any questions about the plan for the class? Okay. So today I want to finish our discussion of angular momentum. Angular momentum, sometimes I'll just call it rotational momentum. And we defined it in the context of analogy. So by analogy, the linear momentum is the mass times the velocity. So by analogy, the angular momentum is the moment of inertia, or the rotational inertia, I, times the angular velocity, omega. And we somewhat annoyingly use the letter L to delineate linear momentum. And at this point, I want to point out that since omega can be a quantity that has a vector on it, then L can also be a quantity that has a vector on it. And for the purposes of this class, which there's again a little bit of a swindle here, we're going to treat I as a scalar, just like mass. It's not really true that a body's value of I is really a scalar. It's not quite a vector either. It's a little more complicated than either of those. But for now, that's how we'll treat it. And in most circumstances with the spinning body, say I have, here I have a globe, and there's an axis of rotation that goes through it. And if the body is spinning like this around, say we're looking from the top down, and it's spinning, you can use the curly fingered right-hand rule to basically infer that the linear momentum is pointing along the same axis as the rotational speed, L. So a spinning body has an angular momentum vector, and that angular momentum is pointing upward or downward, or whatever way it's pointing in accordance with the right-hand rule. So again, curly fingered right-hand rule. Curly fingered right-hand rule. And once we've got that, we, by definition, by analogy, can use conservation of linear momentum, angular momentum. So we have conservation of angular momentum if the system is isolated, which is to say the net torque, not the net force, but the net torque is equal to 0. And again, that's true in the vector sense. Then the total momentum, the total angular momentum is equal to the force equal to the total angular momentum of the system after. So the force is equal to after something is equal to something prime. That's true in any one dimension. It's also true in a vector sense. Okay. So that's the basis upon which we continue to move forward. So let's see, what are we going to do with that? I've set that up. There's one other tool I need to set up, and that is, I'm going to erase here. We've got this definition of angular momentum. We've got the conservation of angular momentum. I want to introduce something, and I'm not going to prove it. It's easy to prove. It's a little bit, you can either start with this and go there or vice versa, but I'm going to talk about something. I'm going to talk about the parallel axis theorem. So again, I won't derive it, but it's easy to derive once we start with our definition of rotational inertia. And the parallel axis theorem, first of all, you have to ask the question, what does it actually say? That's actually the tricky part, is understanding conceptually what this is. So I'm going to start with a three-dimensional object. So again, you're going to use the physicist's arbitrary three-dimensional extended object, which I will represent as a arbitrary shape like a potato or something. And through that object, I will define an axis that goes through its center of mass. So if the center of mass point is something like here, so that's the center of mass point, then I can imagine basically running a skewer, defining an axis. So there's an axis that basically goes through the center of mass point and basically comes out the other side. So basically, it's not, there's a rotational axis that's defined in some angle into the potato, okay? And then I could say, well, suppose instead of having a skewering the potato in the center, I skewered it off at some arbitrary location, say over here. But the key issue is that I have to have the skewer the same. The parallel part has to do with the orientation of the axis. It has to be basically parallel to the axis that you've already defined for the center of mass, right? So usually there's an obvious axle and you pick it. So you have this new position here where you've moved, and as you've gone through, you've skewered this. The important dimension is this distance here, which is the distance r. R is the distance from the axis that is at the center of mass to the new parallel axis. So we've shifted the point of rotation from the center to some other spot. So now the potato spins around this axis instead of that axis. So if that's true, then you can apply rotational dynamics to that new axis, but you have to change the rotational inertia that was calculated about the center of mass. So what does the parallel axis theorem says? It simply says that the moment of inertia as a function of I, where this is the displacement of the axis, is equal to the moment of inertia as calculated about the center of mass, plus the mass of that object times that distance squared. So it basically gives you a shorthand formula for recalculating the moment of inertia, the rotational inertia, without having to do a whole bunch of calculus, in the case that you move from one location to another. Okay, so this is nice. So let's do a simple example, which gives us a result that we already know. But a simple example is a thin rod. So if I have a thin rod like this, its length is, again, the length is L and the mass is M. From the center of mass point, I could give you, and again, this comes from the calculus, that the I of the rod at the center of mass is equal to 1/12 L squared. So we start with that. Say we've got this in our pocket. And again, I've already given it to you. But now suppose I want to know what I rod is at the end. Suppose instead of rotating from the pivot point here, I move the pivot point here. So again, the whole idea is you keep the axis parallel, but you move the pivot point from the center of mass to wherever you're going to move it. So in other words, I for rod end, according to the parallel axis theorem, should be ICM, I rod CM plus M. Well, that's a question. Let's actually write these things out. Let's just use that. We'll save ourselves space. So ICM, so we already know what that is. So that's 1/12 L squared plus I squared, where R is the distance from here to here. That's R. But in this case, R is equal to L over 2 because I basically displaced the distance L over 2. So that's 1/2 ML squared plus M times L over 2 squared. Oops, I just need a little bit more room. Don't put a box there yet. So, well, that's not so hard. That's ML squared, ML squared. I got 1/12, 1/12 plus 1/4. So I've got 1/12 plus 1/4 times ML squared, which is just 1/3 L squared, which is the answer we already knew because I gave it to you a week ago. But nonetheless, you could calculate it. And of course, you can use this to calculate moments of inertia for things that you don't already know. So let me do one other example, just so you can get the idea how to use this. Suppose I devised a problem that looks kind of like this. I got a hinge that I'm putting on the ceiling of all places, and then I have a thin hoop that I'm attaching to the hinge, right? And maybe I'm setting up the problem by, I don't know, putting the hoop, somewhat off angle, so that the center of mass of the hoop is here. Something like this. So that's my hoop. That's off at some angle. And so I want to work out, for example, maybe I want to work out what the angular acceleration of that hoop is, right? So in order to do that, I'd have to figure out the torque due to the weight of the wheel. The torque due to on the hinge is 0. But in order for me to actually apply Newton's second law, the third law, if I say tau net equals I alpha, I need to know what I is. and I is because I'm now rotating. I basically put a pin in the hoop. The whole hoop is swinging down like this. This is the path of the hoop. The value, I'm not at the center of mass of the hoop anymore. So I have to say, okay, I, for the hoop at the hinge is equal to, well, what's it equal to? It's equal to I of a hoop at the center of mass plus m times r squared, right? So we just have to figure out what those terms are. So we look up on our crib sheet or our review sheet, I hoop, that's just m r squared. And then m, and then this is the displacement. So I'm going from here to here, but that distance is just r. So that's just m r squared. So this is equal to 2 m r squared. So in other words, the rotational inertia about the hinge is twice what it would be if I were just rotating about the center of mass. Any questions about that? This is just how you might use this kind of tool to recalculate the center rotational inertia. All right, cool. So let's now go to I'm going to erase this, and we're going to go to one more idea for the day, and we'll call it a week. We'll let you go for the weekend. Here's the idea. What about a point mass? What about the angular momentum of a point mass? So everything we've done so far has been for a rigid body. So what do I mean by a rigid body? I mean like an object that has a physical extent. We've basically argued that the angular momentum of a rigid body, it's vector form. I know you can't see that, but I don't want to, we're not going to use it. But we've got this idea that's just equal to I omega. I already wrote this down. Okay, where I is the moment of inertia of that body. Now, if you think about that, okay, so here I have a small marble, and in the limit that this object becomes, the radius gets smaller and smaller, its physical extent goes to infinitesimal. You might say, well, there can't be any rotational inertia because it can't spin. I mean, it doesn't make sense to talk about an infinitesimal point spinning. It's a kind of a strange idea. But what if instead of talking about spinning about its own axis, we talked about the motion of the object in a translational sense, but in a kind of circular sense, right? In other words, suppose the object is basically in orbit, or it's in some kind of, maybe it's in a circle, maybe it's in an ellipse. In some sense of the word, something is going around in a circle. And that rotation, that sense of rotation depends on where you look at it from. So it's a relative sense. In other words, if I'm in the center of the circle, that's a different result than if I'm outside the circle, at least it seems to be. Can we define a rotational inertia, angular momentum that's associated with the particle? And the answer is yes, we can. And the trick to this is twofold. First is, obviously, we want a quantity where the faster it goes, the more angular momentum. And the other thing is we want a quantity that follows the and rule, which is to say, if it's going around in the counterclockwise direction, our hope and expectation is that the angular momentum vector is pointing curly-fingered right-hand rule, basically pointing towards you. And of course, we can get that idea, that same right hand, and this basically comes out of the cross product. So we're going to basically, without deriving it, I'm just going to kind of assert that there is a sense of, there's a definition that basically gives us all the things that we want. So the angular momentum, and I'm going to start with the vector because, so this is the angular momentum of a point mass, so a point particle, okay, is defined as the vector r, where r goes from my pivot point to the mass, That's so important. Again, R always goes from the pivot point. It never goes to the pivot point. It goes from the pivot point. And it always goes to something. Well, in this case, instead of going to the force, it's going to the mass. But then we're crossing it with the vector momentum. That's our definition of point mass angular momentum, R cross P. So let's actually work out what that is. All right, so again, don't forget that what this means is that the magnitude of the angular momentum associated with the point particle, which we just call LPP, that's just going to be equal to R times P times sine of phi, where phi is the angle between the radial vector and the P vector. Now remember, this is for point mass, so it's not a radius necessarily. It's the radial vector that goes from the reference point to the location where we want to have this. Okay, so that's our definition. So let's actually use this definition for some simple examples and see what we get. Notice it's quite a different definition than for a rigid body. It's, you know, it doesn't, at least at first glance, it doesn't look like the same thing. So for example, suppose I have a particle of mass m, and suppose that particle is moving around in an orbit around some object. Maybe there's a planet around the sun or something like this. And I'm going to use that central object as my definition of the pivot point. In other words, I'm going to assume an axis that goes through the plane of the orbit, and that's my reference position for calculating the angular momentum. So that's the pivot point here. And this is m, which is a point mass here. So if we set up the problem so that we know that we've got some particular value of the momentum that way, which is just mass velocity times that mass, and then I can basically work out, draw at least graphically, the vector that goes from the pivot point to the mass. So that's my vector r. Okay. Well, in this case, because I'm in, this is circular motion, right? This is, you know, basically uniform circular motion. In this case, the vector r is perpendicular to the vector p, and therefore the linear momentum, sorry, the angular momentum, it's confusing that L is associated with the angular momentum. The angular momentum associated with the point particle moving in uniform circular motion is equal to, well, basically it's just r times p times the sine of 90 degrees, right? So we have that definition up here. L equals r cross p. So the magnitude of L is equal to r p sine p. So let's just keep that in our heads. So r times p times sine theta, well, sine theta in this case is sine of 90 degrees, which is 0. So that's just basically m times c times r. All I did is rearrange the terms there. So if I have a particle moving in uniform circular motion, the angular momentum of that particle as measured from, as measured from the center of the orbit is just mvr, which is the momentum times that radius, right? So particles moving in orbit have angular momentum. And obviously, if I'm moving with uniform circular motion, that angular momentum is conserved, which is to say, since the speed is not changing, this quantity never changes as the particle moves around. It's not a particularly useful result, but it is satisfying. In this case, do we expect angular momentum to be conserved? Well, the question is there a torque? And the answer is, as long as the forces, well, what would keep a force? What would result in what would result in uniform circular motion? There must be a net force, which is centripetal. And if the net force is centripetal, then the torque, which is r cross f, would always be 0. So it all makes sense. As long as I'm moving in uniform circular motion, the system is isolated to torques. There's no net torque, and therefore angular momentum is conserved. Everything is good. Questions about that before I erase it? I want to do one more example. And then I think we can call it a day. So 2 more examples, sorry. Okay. So now let's do the motion of a particle that is, well, it's not so obvious what so I mean, how do I say, it's not that surprising that an object going in a circle will have angular momentum because something's going around. What about an object that's going in a straight line? So we'll set up the same kind of situation. I got a particle of mass m, and this time I'm going to have it moving on a path that is perfectly straight line with uniform speed, right? V, a perfectly straight line. And I'm going to basically ask the question, what about the angular momentum of that particle? Well, you have to pick a pivot point. So what I'll do is I'll just pick a pivot point here. I'll just pick a pivot point right here. Somewhere down below this line is my pivot point. So that's the position by which I'm measuring the angular momentum of that particle. So the particle starts here. Sorry, and let's go to pink here. Starts here, it's here, it's here, it's here, it's here. How do I calculate the angular momentum of that particle? Well, again, well, here, I'll draw it over here. What's the key idea? I mean, here's the first thing. If I've got the particle, if I just at the instant when the particle makes a perfectly straight line between this location and this location, so that at that particular instant, R is perpendicular. So at that particular instance right there, L at that particular instance, which is R cross P, the magnitude of L is R cross P, which is R times P times sine of C. Well, in that particular example, that's just R times P, which is just R times M times V. So that's nice, where R is this distance here, okay? And it's the perpendicular distance, okay? So I'm going to call that perpendicular distance, I'm going to call that R perp, because it's the particular value for this particular thing. But what about, for example, with the particle is, let's pick a location like right here. That's moving. So in this case, the vector R goes from here to here. So obviously R is a different value. So the magnitude of L in this case, again, this is the point particle, is equal to R times P times sine of phi. So what I'm going to do is I'm just going to rearrange the thing on the right-hand side a little bit. I'm going to just call this, I'm going to say this is R times sine of phi, this thing, times. Well, R, this is R, then this distance, if that's sine of angle, what is the angle? This is R. So that means that if momentum is pointing this way, so again, that's the same direction as V and P, then the angle between R and P is this thing right here, which I call phi. That's phi. But if I use the trigonometry of this triangle, then this thing, which I called R perp, that is R sine phi. That is R perp. So that's equal to R perp times MV, where R perp is defined as R times sine of phi, anywhere on the path. So notice, this is the angular momentum here. This is the angular momentum here, in the special case where it was easy to calculate. And everywhere I calculate, it's the same thing. So the particle moving by has a angular momentum whose value is the same everywhere. So it's conserved. It's not changing. It's the same value here as here, everything. And its value is equal to the momentum times the shortest perpendicular distance from the pivot point to the line. This perpendicular distance sometimes has a name. It's sometimes called the impact parameter. It's basically how close you get to the line. And often it's given the symbol little b. Don't know why, but that's what it's often given. But the key issue is this is by definition an isolated system. So because there's no forces on it, the net force is 0. It's moving in a perfectly straight line with constant speed. So by definition, the net torque, no matter what point I pick, the net torque will be 0. So I'm not surprised to learn that the angular momentum is perfect. Okay. Questions about that? So the key idea is that for a point particle moving in a straight line, all you have to do is find the perpendicular radius to the line, multiply it by the momentum, and that is the angular momentum. So you multiply that radius times the linear momentum to get the angular momentum. This conversion between linear momentum and angular momentum only works for point-like particles, not for rigid bodies. It's a little more complicated for rigid bodies. Questions about that? I'm just going to go to one more example and we'll call it a day. All right. So this next example corresponds to a problem that I'm going to set up, but I'm not going to completely solve it. It's relatively easy to completely solve it, and I will write it out as a practice problem. But I'm just not going to do the whole thing because it's algebra. But okay, let's set up the problem. So here's an interesting problem. The key for the whole problem is how do you tackle it? So here's the idea. I got a hinge, again, attached to the ceiling. Hinge. And then I've got a rod. So here's my rod, a thin rod of length L. So length L and mass M sub R. Okay? And it's just hanging. Nothing happening. I mean, it's free to swing on the hinge, you know, so it looks like this. Let's make sure we got the idea. So it's free to swing on the hinge like that, but for starters, it's just hanging, motionless. But then comes along a blob of clay. A blob of clay, a small blob of clay. Why small? Small enough so that I can treat it as a point object. Why clay? Clay because clay is sticky and soft, and if it hits the rigid rod, it will stick. And indeed, that blob of clay is coming in, and it's going just before impact. The blob will have a linear speed, which I will call V naught, and it will have a mass, M sub B. So M sub B is given and V naught is given, and basically I've got an impact of this blob on the end, the very end of that hinge. And the impact happens, and as a result of the impact, the blob sticks and the stick swings up with some initial angular speed. Okay, so up it goes, whoop, or rather some angular speed, which I'll call omega. We'll call that the angular speed right after the impact. So I'll call it, I don't know, I'll call it omega prime. Okay, I'd like to know what that is. All right, so let's do the mental exercise. You're taking the final exam. The problem is set up this way. You got to figure out what you're going to do. You've got the whole semester of material to deal with. What objects, what concepts can you use? So let's go through the mental map. You can you use kinematics? No, because you certainly aren't given either the velocities, either of these velocities is a function of time or position is a function of time. You can't take derivatives. You can't. There's no I hats and j hats. That's no good. So kinematics, at least for now, put it aside. Can you use Newton's laws? Well, it wouldn't be hard to figure out what the hinge force is before the collision, because obviously it compensates for the weight. But I'm not interested in the hinge force. I'm interested in omega. I don't have any idea what the force of this collision is. Anytime I have a collision, I get the willies about using Newton's second law because I don't know what those forces are. You might say, well, if I knew the forces, I could calculate the torques. And if I knew the torques, I could figure out the omegas. But again, I don't know the force. So I can't use Newton's second law in a linear way. I can't use it in a rotational way. I don't know the torques. I mean, they're there. Obviously, something is going to cause this thing to twist, but I don't know what they are. So Newton's second law, no good. What's next? So we did kinematics. We did Newton's laws. No. The next thing we try is conservation of energy. Yes, let's try some conservation laws. Let's start with conservation of energy. And you might say, ooh, well, you know, there's before and after, there's a swing up or something, but I'm asking you, this is immediately after the collision. Immediately. In other words, just as after the collision as it's just beginning to, as basically everything's come to a collision and everything basically starts spinning up. The real problem with conservation of energy is that this collision, because it sticks, is totally inelastic. And you can always immediately conclude that if I tell you totally inelastic, then there's no way you can use conservation of mechanical energy. In other words, totally inelastic collision tells you that the forces of the collision are doing work because they compress something, right? I mean, the only way the blob comes to stick is if it basically, you know, squashes on it. So work is being done. So you can't, and you don't have any way of writing down what the, you know, how that work, but where that energy, what that form of displacement energy is, that squishing. As soon as I tell you totally inelastic, you know, immediately you may not use conservation of mechanical energy. The only collisions where you can use conservation of energy are totally elastic collisions. If it's inelastic, you can't use it. All right, so no conservation of energy. What's left? What about conservation of linear momentum? You might say conservation of linear momentum is great. It's especially useful for totally inelastic collisions. You've got this tool in your pocket. You say, this collision is totally inelastic. That's the first thing you think of. A totally inelastic collision, let's use linear momentum. But the problem with linear momentum, this is the whole business. If you could start doing this. You could, so mv, you know all the masses, you know the initial final velocities. You could start doing the algebra. And if you did that for this problem, you'd be in big trouble. Why? Because for this system, the condition of isolated, for linear momentum, conservation of linear momentum, is the requirement that the net force is equal to 0. Is that condition true here? And the answer is, well, let's figure it out. Oh, by the way, I would always, in a problem like this, there's no, I would say the collision takes place, the before and after are basically very close to each other. So I'm not worried about the vertical motion of the object before. So I'm going to ignore gravity. That would be part of the statement of the problem. So that's even worse for conservation of energy because there's no before and after, no potential energy here, but okay. So ignoring gravity. So what are the forces? So we're ignoring gravity, so we don't worry about the forces on the blob because it's before. It collides. There's a whole bunch of forces it's colliding with. So those forces are not 0, but they're internal to the system. If I define the system as the blob plus the rod, all of this is one thing, right? Then those internal forces don't catch. So far, so good. And you could say, well, before the collision, there has to be a hinge force, but the hinge force is canceled by the weight force. And so before the collision, the system looks isolated, and that looks promising. But during the collision and after the collision, you know the system is not isolated. In other words, isolation doesn't just apply at one point, it applies for the whole collision and before and after. It's not isolated because when this thing hits this, you know, what's it going to do? It's going to try to, you know, it's going to basically apply a force here and a force here. And relative to the center of momentum, there's going to be a torque, which is to say, in order for the top end to stay put while this thing swings up, there's going to have to be a force on the hinge that holds the top in place. We don't know what that force is, but we know it has to be there. So there has to be at least a horizontal force on the hinge. And furthermore, if this thing's swinging up, then there's going to be then the bar is moving with centripetal acceleration. There's got to be a net force upward. So again, the hinge force is not balanced by the weight force during and after the collision. And therefore, this system is not isolated to net force. And therefore, I cannot use conservation of momentum. You could set up the problem, you could plug in the M's and the B's, and you could get an answer, and it would be wrong because you haven't met the condition. And you don't know what the force was on the hinge. So what's left? The only tool left in your box, the only hope you have is conservation of angular momentum. So we have to check, is the system isolated for conservation of angular momentum? And again, we're ignoring gravity. Turns out gravity doesn't come into this question. Well, it sort of does, because there's a force of gravity on the bar, but the force of gravity relative to the hinge, you know, the gravity force is basically pointing this way. So again, what are the definition of torque? Torque is defined as R times F times sine of the angle between them. So for the weight force, which is applied at the center of mass, the radius vector comes like this, and the weight force basically applies in that direction. So they're parallel. So since they're parallel, the sine of phi in this case is equal to 0 degrees. So the torque due to the weight is equal to 0. Yay! The torque due to the hinge force, if I choose the hinge as the pivot point, then the torque due to the hinge also has to be equal to 0. Doesn't matter whether we know it or not. And then there are torques that result from the forces of interaction between the blob and the stick, but by Newton's second law, all those forces are equal and opposite and applied at the same location, so they also total to 0. So in this case, we can say that no, the system is not isolated for forces. The system is isolated for torques, and we can use conservation of angular momentum. Yay! We have a way out. We can solve this problem. So let's start to solve the problem. I'm not going to solve the whole problem today, but I will set it up. I've defined the system already as the rod and the stick. Notice that the system does not include the hinge. Again, what's the key idea of a system? The key idea of any system is that there's no ambiguity about what's in the system and what's not in the system. In this case, the system is the blob and the rod together, not the rest of the universe. So since I know I can use conservation of angular momentum, that means that the total angular momentum is equal to the total angular momentum prime. So that means that basically it's the angular momentum of the blob, which I will label alpha B, plus the angular momentum of the rod is equal to the angular momentum of the blob prime plus the angular momentum of the rod prime. And again, if you set up the problem this far and you don't do anything else right, you'll get most of the points. It's the setup and the concept that are really the most important. All right, so the angular momentum of the blob, well, the blob is a point-like object. And again, I'm making a measurement relative to the thing. So in other words, I'm going to basically say, you know, the angular, I'll put this over here, the angular momentum of the blob, its magnitude is just equal to R, you know, again, the usual story, R times P times sine of theta, T rather. Well, what is that here? That, so I've written that down, but just to remind myself, let's actually write it down here. So So therefore, the angular momentum of the blob is r, where r is the distance from the pivot point to the blob, which is just the length of the rod. So that's L. We'll call that length L, right? That's what we did. Times the momentum of the blob, which is just m sub d times v naught, times the sine of the angle between the momentum, which of course is in this direction, and the radius, which is in this direction. So that's a right 90-degree angle. So sine of 90 degrees is just 1. So we get m, we could just get L times m times mb times v. And if you want, again, it's just mrv. It's the same thing. Plus the angular momentum of the rod, which is just I times the initial omega. That's omega prime. But the initial omega is just 0. So that's just 0. And then that's equal to, well, we're swinging off. So at least at that instant, right after the impact, I've got a new velocity v prime. So that's just going to be equal to L times m times v times v prime plus I, which is the I for the rod, times omega prime, which is what we want. So again, I got this expression for the point mass and this expression for the rigid body. For the rigid body, I use I omega. For the point mass, I use R cross P, which in this case is L times MBV. So let's carry on with this. So we get L times MBV is equal to L times MBV prime plus, well, it's a rod, and then let's see, what's the story with the rod? I'm at one end, so I have to, since I'm rotating about the end, I have to use 1/3 times M rod times L squared times omega prime. Sorry, this should be an L. So hard to see. So I'm all set. I could solve for omega prime. What do I know? I know L, M, V, that's good. M, L. Oh, I don't know V prime. I've got to get a handle on V prime. Everything else except for omega prime I got, but I got to get V prime. How am I going to get V prime? How do I get rid of this V and turn it into something that depends on omega? Anybody have an idea? What's the last tool we always pick up when we're doing these rotation problems? The one last step.
Rolling constraint.
The rolling constraint, yes, exactly. So one more time with the rolling constraint. So let me just erase this so we can remind ourselves about the rolling constraint. So the rolling constraint says that V is equal to omega R, right? So again, there's an alpha version and the V version. So in this case, I just put primes on those guys and I change the R to an L. So I can just substitute that in. So let's do it. L times MB times V is equal to L times MB times that's going to be V prime, which is just omega prime L. Yes? Times that, so that's cool. And that's equal plus 1/3 times M sub R times L squared times omega prime. Yes? So notice that I'm not going to finish, but at this point we just solve for omega prime. It's just algebra. I could do it in 3 minutes, but why bother, right? I've got these two terms. You have to pull out the there's an L squared. Yeah, you're good, but one of them, one L, this goes. One of these L's cancels. The MBs and the R's come and make a ratio. You get a V naught in there, and you end up with an expression for omega prime. It's just algebra. I will do that on the practice problem so you can see. That's all I've got for today. So again, conservation of angular momentum. It's the last tool in your toolbox, but might be the only tool in your toolbox to solve a particular problem. Especially when you have a collision that involves a body that has a fixed pivot point, like a rod on a hinge, or I could have thrown the blob at a massive pulley. There's all kinds of problems where the hinge wrecks conservation of linear momentum, but allows conservation of angular momentum. So consider that for this kind of problem. And then writing, once you've got this far, once you said, okay, before and after, the tricky part is just breaking these terms down one at a time. And again, for the rigid bodies, you just want I omega. And for the point masses, you want basically, again, the key idea is that alpha point mass, point particle is equal to R cross P. That's the magnitude of that, which is R times P times sine of phi. So as long as you've got that in your pocket, you can do these kinds of problems. Questions? And with the one exception of doing a simple gyroscope, which we will take maybe 10 or 15 minutes to do by Monday. I haven't decided whether I'm going to do it synchronously or asynchronously. We're done with rotations. That's it. Whew. Otherwise, anybody has any questions? I will have office hours today at 6 o'clock. No office hours tomorrow, but I will have office hours Saturday and Sunday, so I'll post them. And if you have other questions, or you need to check with me about anything over the weekend, don't hesitate to send me an email. And otherwise, have a good weekend.